So as Frank said, it's very early here in Mexico, so I hope I won't say anything wrong. That's the first warning. But the real warning is that this work is not published yet. I just finished this recently, as I did a sabbatical year at the University of Picardy. I just finished it, so this is very recent work. It's not yet published, so but I hope everything is correct. Okay, so let's see. Okay. So the talk is going to have these parts. First, I'm going to explain what the title means, where is the place I'm working on. Then I'm going to define these home functors, which are going to be the key part of the construction. And so these home functors are going to allow us to define the Hochschild cohomology functors. I'm going to say how we change resolutions in this context, and so I can give you an example. And then finally, something wrong. And then I'm going to just give you a list of classical results we can recover in this context I'm working on. So the setting is going to be, R is going to be a commutative ring with identity. And then this X is going to be an essentially small symmetric monoidal category enriched in R mode. So what does this mean? So let's talk about the set theoretical conditions we have in this category. So essentially small, you probably all know, it means that when we take a skeleton, the skeleton of this category is a set. So this category is not so big, it's not small, but it's essentially small. Then enriched in R mode means essentially, just to give an idea, it means that these sets are R modules. It also means, of course, that the composition is bilinear, but let's say the main idea is that they are not only sets, but they have a structure of R modules. Okay, this is, let's say, the set theoretical conditions, and then the more important conditions is that monoidal. Monoidal means that we have a functor from this product category to X that gives us, this functor gives us a product. In this case, we have to add the condition of this functor being R bilinear because of the condition we put on the set. When we define monoidal in general, we only say a functor that gives us this product that we call a tensor product. But in this case, we have to add the linearity condition. So it behaves well with the rest of the category. And this product, this tensor product, is associative, and we have an identity object. There are more conditions than, again, when we define a monoidal category. We have certain axioms that we need, but I'm not going to give you the whole list. The main idea is that we have a product that is kind of a tensor product. I don't use the symbol of a tensor because I'm going to use that later. And of course, the identity behaves as an identity, tensoring by one, and gives us essentially the same object we had before. But we also ask for this product to be symmetric. This means essentially this, that this tensor product is commutative, let's say. Then again, it's more and more than this, but the main ideas are this. So we have everything, essentially small, symmetric, monoidal category enriching. So under these conditions, with these conditions on X, when we consider the category of R linear functors from X to R mod, because this is what I'm interested in, the category of functors from X to R mod, this category is, of course, an abelian category, because we're going to R mod. But it is also, it turns out to be also a symmetric monoidal category, also enriched in R mod. It is no longer essentially small, of course, but it has a tensor product that is also symmetric. And this is denoted in this way. And so I'm not going to tell you how this tensor product is defined. It's defined by something that is called Bayes convolution. It's kind of complicated to explain. Well, not complicated, but it will take long. But the idea is that we don't really need to know how this tensor product looks like. It can be described in a way, but it's kind of complicated. But for the purposes of the talk, we really don't need to know how this tensor product looks. We only need to know we have this tensor product, and that is also symmetric, and the identity is given by the functor when we take in the one of our original category. Okay, so we can make a product of functors. That's the main idea, and it's symmetric. That's all we need to know. So why we're considering these kind of categories? Well, let's see some examples of X. Well, first of all, the tensor product we all know is the tensor product of modules. So an example of X can be the category of finitely generated R modules, with the tensor product being the usual tensor product, and the identity being the ring. For the purposes of the talk, I'm adding here finitely generated because I asked that my category is essentially small, but of course, if we consider only the category of our modules, this is a monoidal symmetric category. So this is like let's say the example we always have in mind when we think about tensor product. But the categories I'm interested in, there are many other examples of this situation. For example, if we consider the category of correspondences between finite sets. What I mean by this, let me just write a little bit. Of course, the objects are finite sets, and the arrows we're considering from one set to another. An arrow can be a correspondence that means only a subset of the Cartesian product of these two. That's it. So an arrow from a set to another one is just a subset of this Cartesian product, written the other way around, so everything works fine. And so we consider all these correspondences, and we can take the free R module with basis on these correspondences, and we have our sets. Of course, we have to define a composition between these correspondences, but this can be done. We have identity arrows, etc. So this is essentially small category, and the monoidal structures. We have two possible monoidal structures in this example. So we can take the disjoint union. If we take the disjoint union of two finite sets, we have a tensor product that is symmetric. Or we can take, maybe can be more natural, the Cartesian product. This Cartesian product also gives us a symmetric monoidal structure. In the first case, the identity object is the empty set, and in the second case, it is the object with the set with one element. And so these categories, we can consider these two monoidal structures, but what has been studied is the first case, when we consider the tensor product to be the disjoint union. For this case, the category of functors, the corresponding category of functors, has been recently studied by Serge Bouc and Jacques Thévenard. They have done a series of papers where they study the structure of this category F, simple functors, etc. So this is one example of the situation, but the example I'm interested in myself is the biset category. So again, just let me give you an idea. In this case, the objects of the category are finite groups. And the arrows we are considering, let's say, from a group H to a group G. So what we consider as arrows are the G cross H opposites. So this is just a group. H is a group, G is a group, but we write this like this because we like to consider this as G cross H subsets as what we call G H bisets. So the idea is that we have an action of G on the left, an action of H on the right, and these actions are compatible. And so instead of considering morphisms of groups, we consider these bisets as arrows in a category. Formally, what we're taking is actually the Born size group of G cross H. So this is the Grothendieck group of this category of bisets. So the idea is that we consider bisets as arrows. So this is the example I'm thinking of. So again, we're considering this arrow, so we have to define a composition, we have to define identity morphisms, everything works fine. This is essentially small category. And the monoidal structure is just simply given by the direct product of groups. So in this, with this situation, we have another example of X. So there is a question. What is the element structure on these bisets? Yeah, that's what I was. Actually, I didn't write it completed. What we're considering for morphism is actually the bonsai ring with coefficients in R. So this is R tensor over the integers, just the bonsai group. So the bonsai group is an abelian group. So we're tensoring by R, and this is an R module. Okay. Okay. So the monoidal structure is just given by this direct product, and the identity object is just the trivial group. And so in this case, the corresponding category of functors is called the category of biset functors, and also it's been studied a lot in recent years. It has proven to be a useful tool when working with the representations of finite groups. So that's why we were interested in this. And in this case, the identity functor that we mentioned before is precisely the bonsai biset functor. So this is where I like to work on, but I realized I didn't need the whole structure of the biset category to define this Hochschild cohomology construction. So that's why I decided to work in a more general setting, only considering all these conditions, essentially small symmetric monoidal. But the example I have in mind, the examples I would like to work on is these biset functors, belong to these biset functors. And there are other examples of these conditions in X. There are many examples one can consider. Okay. So when we were working on these monoidal categories, we can define what are called monoids. So a monoid, an object in F is called a monoid if we have a morphism mu that we can see as a product in A, and we have a morphism E that we can see as an identity that satisfy the following diagrams. So the first diagram, what it's saying is essentially that this product mu is associative. So I also want to note here that for the identity arrow of an object, I only write A. Also, the object is A, the identity arrow is also A. So here when I say A tensor mu, it means the identity A. So what we're saying on the top is that if we take in the identity and mu, and then we take in mu, this should be the same as taking mu, the identity, and then mu. So as you can see, this says essentially that the product is associative. And the other diagram says that we have an identity, as we have for rings. So on the left, we have this is the isomorphism between A and I tensor A, on the left and on the right. And what we're saying is that this morphism E behaves as an identity. Okay, so I'm taking E and the identity, and then mu, this should be the same as just the isomorphism of the identity. So, as I said, the idea of a monoid is like the idea of a ring in a monoidal category. Actually, some people call them rings. I prefer to call them monoids because for me, rings are different things. But some people call them rings. Some people also call them algebras because we have also this idea of an algebra, but I'm going to call them monoids. And so we have, we recover many of the properties of, we have in rings. For example, we can define the opposite monoid. What is this? This is the same object A, but we have an opposite monoidal structure, an opposite product. So what I'm doing here is I'm taking the symmetry, just turning this A from the left to the right, and then I'm taking the product. And so we can say that a monoid is commutative if now this structure that I did the other way around is the same as the one I had before. So another property we can prove is that whenever we have two monoids, again, the tensor product of these two monoids is a monoid. These kind of properties that, I mean, we have the parallel of rings. We can define also a morphism of monoids, etc. We have many structures as we have in rings, many properties and definitions as we have with rings. So one of them, whenever we have rings, we have modules over rings, so we can define modules over monoids. So if we have a monoid, what is a module, now is an object, and we have this morphism from A tensor M to M that we're going to think as an action, it's kind of an action of A over M, with the corresponding commutative diagrams. So as, again, is the same idea. On the left, we are saying that this action mu is compatible with the product. This action mu, sorry, is compatible with the product we have for A. So here we're taking the identity and nu, and the nu, this must be the same as taking the product mu of A, and then taking the action mu. That's the associativity of the action, let's say. And on the left, we also have, since I'm defining this as a left A module, so we only take the product of the identity on the left. This should be compatible with the morphism E we had at the beginning. Okay, so again, we can, so these are left modules, let's say, we can define, first, of course, we can define morphisms of modules. These are what you imagine these should be. So A modules form an abelian category 2 with these morphisms. We can define right modules, and we can identify it with left modules for the opposite monoid. Also, if you have another monoid that I call it C because B is already taken for the Burnside functor. So let's say we have C, another monoid, we can define by modules in the obvious way, action on the left, action on the right, compatible, and we can identify them with this monoid that is a tensor product of these two. Okay. So let's leave these modules here for a moment. And so let's talk about these functors. So to define these functors, I'm going to go, let's say, by levels, so we can get to the definition of an internal So the first level is here. Whenever we have an object in X, we have, sometimes I'm just going to say functor, but all the functors I'm working with are linear. So that's why it is in parentheses. All my functors are linear. So we have a functor given by tensoring with X on the right. So we send an object Y to Y tensor X. And we send an arrow also to tensoring with the identity arrow of X. So it's very simple. I'm only using the monoidal structure I have in X, and I'm multiplying, let's say, by an element, by a fixed element. So this is a functor. And so whenever we have an object and we consider this functor, if we have a functor in F, then the shifted of F by X is simply precomposing with this product. Okay, so this is, the shifted is going to be a new functor in F that if you, what are we doing? The evaluation in F is only going to be, it's always going to have this X on the right. Whenever we have an we evaluate F in an object or in an arrow, this X is going to appear on the right. It's always going to be multiplying on the right. That's all we are doing, okay? And so we have a new functor, a new object in our category F. This construction defines actually an end of functor in the category F. So is defined in in objects like this, and we can define it in arrows in an obvious way. We call this construction the Jonet address construction, or just simply the shifted of F. And also, if we have an arrow in our category X, we can define a natural transformation. So C is going to go from Px to Pw. It is defined in an object, again, only by tensoring, this time when tensoring by this arrow on the right. So this is the identity of Y, we're tensoring this arrow identity by C. It's the same idea as in objects, but now we're taking in arrows. So this defines a natural transformation between these two. And in turn, this of course defines a natural transformation now in these two. How? Well, as usual, we just applying our functor F to the arrows we defined before. Okay, are there any questions? No. So again, I go to the other level. So that's why I say I started on the level of X. Now I'm going to the level of F, let's say. So in turn, this defines a natural transformation at the level now of the Jonet address construction. So it seems that we are adding and adding stuff, but once you write this from the definition of the shifted, is very simple. Everything is just follow your nose. There are not too many things you can do to go from one level to another. And so this actually defines a functor from the category X to the category of end of functors of F. And this is all we need to define these functors. So whenever we have two objects in F, by this whole construction we did before, we have now our linear functor from X to F. What is it doing? It's just shifting, and we're just shifting n by all the elements in X, and we're doing as it's defined here in red, and the corresponding thing in arrows here also in red. And so we can define, so we denote in this way, the new functor we obtain in F when we compose these two. So what we're doing at the end is we're taking the in our category F, but with respect to the shifted of n. So m is fixed, let's say. And when we evaluate, what we're doing is we're shifting n by all the elements, by all the objects of X and all the arrows. So the composition of these two gives me a new guy here in F. So this construction defines now a bilinear functor from here to here that we call the internal functor. And so I say we call it the internal functor, but it's not only that we call it that way, but it is the internal functor. What I mean by this is that the tensor product I didn't define before has this as a right adjoint. So this is actually an internal in this category. So the internal is defined in category theory in a more general way. We defined it as an adjoint of the tensor product, etc. It may not exist. But in this case, what I really like is that we have an explicit description of this functor. We can say exactly how it looks like in each object and in each arrow, and it's defined in a very simple way. Okay, so this is indeed an functor. An internal I mean. And also the good thing is that all this shifting we just did here can be also restricted to the case of modules. So if we have a monoid in F, now we want to consider a modules. And so what we can prove is that if we're in the situation before, we have objects and an arrow, we consider these Jonet address constructions as we did before. Then this shifting defines a functor from X also to the category of our linear endofunctors of A mod. So what we're mainly saying is that all this shifting we did before can be restricted to the case of A mod. That is, if I have an A module, the shifted is again an A module, and this behaves well with the morphisms of A modules. And so in this the same way, now if we have two A modules, we can consider again this functor from X to A mod by the previous construction we did before. Sorry. And now we denote in this way the object in F defined again by the composition of these two functors. So I'm taking the shifted of N again, but now, of course, I'm taking only morphisms of A modules. And this gives me a new functor in F. This correspondence is again a bilinear functor. Okay. Okay, so this is again we need the side of functors of this category F. And so the following, the next construction I'm going to do, it works in general in any monoidal category. So we're going to fix A is going to be a monoid from now on, a monoid in F. And we can consider this complex in F. But again, this works in a more general context. This works in any monoidal category, actually. We don't need to be in F. This works for any monoid in any monoidal category. So this is, as usual, we're considering this A tensor 2 means, of course, the tensor of A with itself 2 times. Okay. So we're tensoring A with itself 2 times, 3 times, n times, etc. A2 is in degree 0. And we define these morphisms as in the usual way. So this is di. What we're doing, we're taking the identity. And in the position I, we're putting this product we have for A, this mu. Okay, so it's identity, mu, and then identity. This is the I. And as usual, we consider this alternate sum of this di. This is the arrows B. This is the standard construction, the usual construction. We can put the augmentation of this complex. As usual, we put A in degree -1, our product mu, and then 0 in the rest of the degrees. As usual, as we do in the classical case, we denote this complex now in this way. And of course, the proposition is that this complex is a resolution of the AA by module A. We call it, of course, a bar resolution. This, I insist, is not only what we do in rings. This can be done in any monoidal category. It has nothing to do with it. Okay, actually, there are actually recent articles that deal, of course, with the Hochschild cohomology in monoidal categories and different settings. But what I like of this situation, again, is that we have these functors. So as we have this as usual, this works in general, of course. So some notation before continuing. So we're going to denote again, as usual, this A tensor A up by AE. And whenever we talk about AA by module, we're only going to say A by module. Okay. And so with this, we can give finally our definition. So we have a monoid in F. We consider an A by module. And so the Hochschild chain complex is the complex in F given by taking this we defined before on this complex. Okay, so our complex this is a complex in F. We can consider, and it's a complex of bimodules. So we can take this of bimodules we defined before with respect to M. And the good thing is that since F is an abelian category, we can define the Hochschild cohomology of A with coefficients in M as the cohomology of this complex in F, whatever it is, okay? So we have our bar resolution. We take in the ohm we defined before. This gives us, again, a complex in F. This is going to be a complex of ohms in F only. F is an abelian category, so we can take, we have subfunctors, we have quotients, we have everything we need. We can define the cohomology. And so this cohomology is going to be, again, a functor in F. So the thing is going to be an object in F again. So this defines a functor from the category of bimodules to F. Okay. Any questions? So one thing I didn't say just before is that this ohm we just defined, I said it lives in F. From the definition, it's only an object in F. But of course, we have the situation as we have in the classical case. If you know, whenever you have we take the ohm with respect to a bimodule, then the ohm has a structure of a left module or a right module. It happens the same in this case. For example, F has another structure. We can take out the structure of M. So what I mean is this, by definition, is just an object in F. And so the cohomology also is just an object in F, but it can have another structure. If our objects have other structures, this can be also a module on the left or on the right. It can be also a bimodule. And of course, it is the case of the cohomology too. But the definition is just as this object in F. So this is very nice because since this ohm is very explicit given by this shifting, this allows to do the calculations of this on this cohomology also by considering only this shifting. It really allows to work in a very similar way as we do in the classical case. In many senses, it behaves as in the classical case. Well, as you know, sometimes this bar resolution is very nice to give the definition, but it's not very nice to work with. So of course, sometimes we need to change the resolution we're working with. And so there are many ways, again, of changing the resolution. I'm going to consider the following. So we're going to consider these two functors. This is a functor of restriction. It's just the forgetful functor. We also have a functor of induction. So again, A is just a monoid. So restriction is just the forgetful functor. Induction is we send either an object or an arrow to tensoring by A on the left, and this gives me an A module, morphism of A module. And it's easy to see that these two functors are adjoint. Induction is left adjoint of restriction. And so with this, whenever we have an adjoint pair like this, we can consider the following definition. So this is the definition. What does it mean to be projected with respect to the restriction? And my reference for this definition is a search book, but I know there are many ways to define it projected with respect to something. So you may say this definition already appears someplace else. This is possible, but the reference where I found this book, I'm not saying it's only him who has defined this. So we say that a module is projected with respect to this restriction if whenever we have a diagram like this in a mod, but such that the restriction of alpha is a split epimorphism, then there exists an arrow from M to X that makes this diagram correct. A restriction is just a forgetful functor. So we're forgetting the structure of a module, and we're just considering this as an object in F. Mm-hmm. Okay, so this is a more general definition, but I'm just putting it in the setting I'm interested in. It can work in, can be defined in any other context in which we have something like restriction, something like induction. So it can be defined in a more general way, but this is the way I'm going to use it. Okay, so let's consider this restriction and induction, but now for bimodules. So what we can show is that whenever we have, and this is again a lemma of an interpretation of a lemma of such book. If we have bimodule, then we can find a resolution for M in which each of these objects here are projected with respect to the restriction. So these are all bimodules, of course, but they are projected with respect to restriction, and such that the restriction of the whole complex is an exact split complex. And moreover, this resolution for M is unique up to homotopy. Okay, you will say, well, very nice. Why are we doing all this? Well, the good news is that the bar resolution of A satisfies these conditions. The bar resolution is as in this lemma. And since this resolution is unique up to homotopy, that means I can sometimes change or find another resolution, maybe more friendly, that is going to be homotopy equivalent to the bar resolution, and maybe I can work with that one. As usual, the idea here is maybe not to work with the bar resolution, but with something homotopy equivalent that may be more useful depending on what we're doing. And so just to give you an example of how we use this changing of resolution, we consider the case of separable monoids. So we say that A is separable if this product we have for A is a split epimorphism. Again, is the usual idea we have for rings. And so, of course, what we want to prove is that if we have a separable monoid, then for any bimodule, these Hochschild cohomology functors we just defined are 0, always. And in the other way around, if we have a monoid such that this degree 1 is 0 for any bimodule, then A is separable. And so again, the idea is that to prove this with the bar resolution may not be a good idea. This is a way of doing this. There might be another ways, but this is the way I like. So I'm going to just give you the proof of the if situation. This notion of projected with respect to restriction is used in both parts of the proof, but the other one is a little bit more complicated, longer. But as you will see, this direction is very easy to prove once we have this way of changing the resolution. So we are supposing that our monoid is separable. That means that we have this split short exact sequence, right? Of bimodules. All these guys are bimodules, since mu is a split epimorphism. We have this exact sequence. And it's very easy to prove, it's not complicated to prove that this is a resolution of A as in the previous lemma. Essentially, what we have to show is that all the guys that appear here are projected with restriction, and this is not complicated. And so, since this resolution is contractible, and we say it is unique up to homotopy, then the bar resolution is contractible, and then our Hochschild complex is contractible, and so we obtain the result we're looking for. So as you see, we have this very easy. If we were trying to do this directly with the bar resolution, we will be stuck for a while. Okay. So with this result, we have a first example, because this implies, in particular, that the identity, this identity functor, this on functor that is the identity, this I, is of course separable. This is very easy to see from the definition of monoidal category. And the bimodules in this case are precisely all the objects in F, So this means that these functors are 0 for any object in F. But also we can show that if we have a monoid that is a quotient of I, this monoid also is separable. This can be shown actually in a more general setting. So this guy is separable. And so it means that also whenever we have quotients of I, these quotients are going to have this property too. That means that all these functors we define are 0 for any C by module M and every I bigger than 0. And so the example is an example in the context of biset functors, because as if you remember at the beginning, we said that the I in this situation of biset functors is the Burnside biset functor. So the translation of this property for I is precisely this one. So this is 0 for every other biset functor, F. And also, if we consider this other functor, this is the functor, now we're taking a field of characteristic 0, and we're taking the biset functor of rational representations. This is known to be a quotient of the Burnside functor. It's a very old result in the theory of representations of groups. It is also a monoid, it's a commutative monoid. And so we can say this in a more precise way. So in this case, we're going to have that this is 0 for every KRQ module M. In this case, it turns out that the bimodules for these functors are precisely the left module, so we have this result. So this is my first example. Very happy when I found it. Okay, so the rest of I'm going to do a quick list without any details. So this is the example I do with more details. So the rest is just a list of what we obtain. So whenever we have these two guys, so in degree 0, we obtain the commutant of M over A, which I didn't define, but it's a generalization of the classical case also. In degree 1, we obtain as usual derivations of A to M, which I didn't define. Modulo inner derivations. Again, this can be defined in a very explicit way, thanks to these ohms. As in the classical case, this has a Lie-type structure. We can define this bracket that behaves like a kind of a Lie product. In degree 2, we also have extensions, Hochschild extensions, which I didn't define, of course. And finally, also, well, not finally, still, we also have that each of these functors is also a module over the commutant of A, which I didn't define. In the classical case, we have that these are modules over the center of A, but in the context of monoids, the center is a different thing. So what looks like the center is the commutant of A. And so again, we have this structure. Each one of these is a module over the commutant. And finally, if we consider this coproduct, so we're taking these functors on A, and we're taking the coproduct. This is an object, again, in F. F is a category with products. So this guy, again, has a struct of a graded monoid, just as in the classical case. The classical case, of course, is a graded ring. So in this case, it's a graded one. And so there are other things I didn't consider, of course, like the Gastenaber structure. I'm pretty sure it can be written in this context. I just didn't do it. The description of in degree 3, H3, we have a description in terms of cross modules, something like that. I'm pretty sure it can be done. It can be done in this context too. I just didn't have the time to do it all. And so this is all I want to say. Thank you.
Thank you very much, Nadia, for the nice talk. So we should thank. Are there any questions? Just trying to see anybody has a question in the audience. Just unmute yourself and start asking. Well, I had a question. I mean, I guess you also have tools to calculate in particular situation, like some kind of filtration, spectral sequences, and things like this for these. I mean, it looks like a very general constructions. So you can develop all these classical tools, I guess, in this setting. I mean, you mentioned Gerstenhaber structure on it. So you can.
Yeah, as I said, there are many things I haven't done yet, but I think you can generalize a lot of things into this context. Yeah.
And so you can study deformation theories also in this setting.
Well, maybe I haven't really thought about that. When we're going to do now with the search book, we're going to try to apply this to particular green-based functors. We really would like to calculate the Hochschild cohomology functors in some examples. But of course, there are many directions one can go once we have these definitions.
And you can get really concrete calculations with this machinery also.
Yeah, that's what we're hoping. Yeah, that we can calculate in explicit ways. Well, that's what we're hoping.
I mean, these symmetric monoidal categories come up also in a lot of algebraic topology contexts of, I don't know, let's say, if you're in homotopy theory, are there modifications of this machinery to get maybe some interesting algebraic invariant in this direction?
Well, the thing is that this is really very new, so I haven't had the time to look at. Actually, of course, I look for other constructions. There are other constructions of Hochschild cohomology in the context of monoidal categories. But yeah, the problem is that sometimes they are not easy to calculate. They're just kind of abstract. So this may be a tool to to calculate more easy other things. Yeah, but what I haven't tried that is the thing.
Okay.
Yeah,
I have a question. So I guess one particular example or application is when you have a commutative ring, and then you have Hochschild cohomology in the classical sense. Yeah. And are they then, I mean, isomorphic? I mean, is that what you recover in your construction, or is it?
Yeah, that's a question I just thought recently. Then there must be a way to link them both, because actually when we have these monoids, there is also a way to introduce rings in the same context. Of course, the rings can be a particular case of this. So yes, I'm hoping there is a way, but I haven't got the time to write it down. It just was a question somebody asked me recently. And so of course, it's a good question. There should be a link between them, but I just don't have the answer at this precise moment. But there should be a way to link them, of course.
Okay, and then I had a second question. What about Hochschild homology?
Yeah, but the thing is that the tensor product is complicated in this context. That is a problem. The advantage is that this home function, the internal lom, is very easy to work with, but the tensor product is complicated. But sorry?
But it exists.
It exists, yes. Actually, we can also define the tensor product of bimodules, everything. But it exists again in a categorical level. It exists like in the very abstract definitions. But we're hoping to maybe try to write it down, at least in some cases, so we can maybe do homology. Yeah.
Is this related to these gray or box products, which also come up in equivalent homotopy theory sometimes, or the construction?
I don't know if it is really linked to that. I don't know. I really don't know. Maybe, but.
And can you construct a cyclic version of this either? I mean, to make a cyclic bar construction and then.
Yeah, it should be possible. It should be possible to do that. I haven't done it yet, but it should be possible to. No, I haven't tried.
Any more questions from the audience? I don't see anything in the chat.
Very nice talk, by the way.
Thank you. Thank you.
So let's thank Nadia again for the very nice talk.